May 3rd, 1945. Nordhausen, Germany. The Mittelwerk Underground Factory. Dr. Ernst Steinhoff stood in the darkness of Tunnel B, staring at a document he could not believe was real. He was 41 years old, a rocket scientist, one of Germany's leading experts in guidance systems and aerodynamics. He had devoted the past 5 years to creating the V-2, the Vergeltungswaffe 2, the Vengeance Weapon, the world's first ballistic missile, a machine that could strike London from 200 miles away, traveling faster than sound, unstoppable by any defense. The V-2 was a triumph of German engineering. It stood 46 feet tall, weighed 28,000 pounds when fueled, and reached altitudes of 50 miles before descending on its target with devastating effect. It represented the cutting edge of military technology, the culmination of theoretical work that began in the 1920s, refined through the 1930s, perfected at the Peenemünde research facility on the Baltic coast. Germany had the best rockets in the world. This was not propaganda. This was fact. No other nation possessed anything comparable. The Americans had nothing. The British had nothing. The Soviets had nothing. Or so Steinhoff had believed. The document in his hands suggested otherwise. It was an intelligence report delivered by courier just hours earlier, marked streng geheim, top secret. The report described American rocket development programs that should not exist, programs that, according to every assessment German intelligence had produced, were years behind German capabilities. But this report told a different story. The Americans, it claimed, were building rockets. Not elegant, precision-engineered machines like the V-2, but crude, improvised devices constructed from scrap metal, salvaged materials, and industrial waste. Rockets built in university laboratories and automobile factories by engineers who had never designed a rocket before. Rockets that violated every principle of proper engineering, yet somehow flew. Steinhoff read the report 3 times. Each time his sense of unreality deepened. It was impossible. Rockets required precision. They required specialized alloys, advanced guidance systems, sophisticated fuel handling equipment. They required years of theoretical development, extensive testing, enormous financial investment. They required what Germany had, what only Germany had. The Americans could not simply improvise their way to functional rockets using scrap metal and determination. That was not how science worked. That was not how engineering worked. But the report insisted that this was exactly what the Americans had done. And standing in that tunnel, surrounded by the remnants of Germany's greatest technological achievement, with the war collapsing around him and American forces perhaps days away from overrunning this facility, Dr. Ernst Steinhoff experienced the first tremor of a realization that would reshape his understanding of everything. The Americans had done something Germany never anticipated. They had solved the rocket problem not through superior theory or better engineering, but through sheer pragmatic necessity. They had built rockets the way Americans built everything, with whatever materials were available, whatever workers they could find, whatever methods produced results. And somehow, impossibly, it had worked. What Steinhoff did not know, could not know, standing in that tunnel in May 1945, was that the American rocket program he was reading about had begun not in government laboratories or military research facilities, but in places far stranger and more humble. It had begun with physicists using blackboards in university classrooms, with engineers welding steel in automobile factories, with mathematicians working equations on scraps of paper during lunch breaks, with mechanics and machinists who had never heard of rockets but understood how to make things work. It had begun, in other words, with America's greatest strength, the ability to mobilize ordinary people
to solve extraordinary problems. And that strength was something German scientists had never understood and never anticipated. To understand the shock German scientists experienced when they discovered American rocket development, you must first understand the certainty they possessed about their own superiority. This was not arrogance in the conventional sense. This was confidence built on real achievement. Germany had been developing rockets since the 1920s. Wernher von Braun, the brilliant young engineer who would later become the architect of America's space program, had begun his career at the German Army's rocket research program in 1932. By 1937, the Peenemünde facility was operational, employing thousands of engineers, scientists, and technicians. The V-2 rocket was not an improvisation. It was the product of meticulous research, systematic development, and enormous investment. The guidance system alone represented years of theoretical work in gyroscopes, accelerometers, and analog computing. The fuel system required solving complex problems in fluid dynamics and combustion chemistry. The structural design demanded advanced understanding of material science and aerodynamic loading. Germany had solved these problems. No other nation had. Dr. Walter Dornberger, the military officer who oversaw the entire V-2 program, wrote in his diary in August 1943, "We have created something unprecedented in human history. A missile that can strike an enemy city from hundreds of kilometers away, that travels faster than any aircraft, that cannot be intercepted or defended against. The Americans and British possess nothing comparable. Their so-called rocket research is primitive, unfocused, years behind our capabilities. We have achieved what they cannot even imagine." This assessment was not unreasonable. American rocket research in 1943 was indeed limited. The military saw little value in rockets. Aircraft could deliver bombs more reliably and more cheaply. Artillery could provide fire support more accurately. Resources were directed toward proven technologies rather than experimental weapons of uncertain value. The American military establishment viewed rockets as interesting theoretical exercises, not practical weapons. There was no coordinated development program, no dedicated research facility, no large-scale funding, just scattered groups of scientists and engineers working on various rocket-related problems, usually with minimal support and minimal resources. From a German perspective, this confirmed everything they believed about American technical capabilities. The Americans were good at mass production, good at building large quantities of adequate equipment, but they were not innovators. They were not theoretical leaders. They were, at best, competent followers who could copy and produce but not create.
Dr. Theodor von Karman sat in his office at Caltech's Guggenheim Aeronautical Laboratory, reviewing a request from the U.S. Army Air Forces. Von Karman was Hungarian by birth, American by choice, and one of the world's leading aerodynamicists. He had fled Europe in 1930 as fascism rose, bringing with him a brilliant mind and a deep understanding of fluid dynamics and propulsion systems. At Caltech, he had established one of America's premier aeronautical research programs. Now the Army was asking him about rockets. The request was vague, bureaucratic, almost apologetic in tone. The Army had become aware of German rocket development. They wanted to know if rockets had military applications. They wanted to know if Caltech could investigate the possibility of developing rocket-assisted takeoff systems for aircraft, small rockets that would help heavily loaded bombers get airborne from short runways.
It was not a glamorous assignment. It was not well funded. But von Karman recognized the opportunity. He assembled a small team: Frank Relina, a graduate student with brilliance and unconventional ideas; Homer Stewart, a structural engineer; Jian Shusen, a Chinese student who would later become the father of China's space program after being deported during the McCarthy era; a handful of others, young, energetic, willing to work with limited resources on a problem most of the scientific establishment considered marginal. They called themselves the Suicide Squad, partly because rocket fuel was dangerously explosive, partly because their professional reputations might not survive if the project failed. They had almost no budget. They had no dedicated facility. They had no specialized equipment. What they had was knowledge, creativity, and access to Caltech's machine shops and chemistry labs. They began building rockets from whatever materials they could obtain: steel tubes scavenged from construction sites, aluminum sheets purchased from hardware stores, fuel tanks welded together from automobile parts, ignition systems adapted from spark plugs and electrical components. The first rockets they built were crude, ugly, dangerous. They exploded more often than they flew. When they did fly, they flew unpredictably, sometimes spinning wildly, sometimes disintegrating mid-flight. But with each failure, they learned. They refined their designs. They improved their fuel mixtures. They developed better ignition systems. By early 1943, they had produced rocket motors that worked. Not elegantly, not perfectly, but reliably enough to be useful. The Army was impressed. They provided more funding. They authorized the creation of the Jet Propulsion Laboratory, a name chosen because rocket still sounded too much like science fiction to be taken seriously by military bureaucrats. And they asked a question that would change everything. Could these rocket motors be adapted for other military applications? Von Karman said yes, absolutely yes. Given resources, given time, given the freedom to experiment, American engineers could develop rockets for any purpose the military required. The Germans, working with precision engineering and theoretical perfection at Peenemünde, did not know this was happening. They did not know that in a laboratory in California, American engineers were building functional rockets from scrap materials and innovative thinking. They would not learn this until it was far too late. What made the American rocket program extraordinary was not theoretical brilliance, though the scientists involved were brilliant, but practical improvisation. German rockets were built in specialized factories with precision tooling and carefully controlled processes. American rockets were built in automobile plants, university workshops, and repurposed manufacturing facilities using whatever equipment was available. This created a fundamentally different engineering philosophy. German engineers designed rockets to exacting specifications, then manufactured components to meet those specifications precisely. If a component required a specific alloy or a particular manufacturing process, that alloy was developed and that process was implemented regardless of cost or time. American engineers designed rockets around whatever materials were available, then adapted their designs when those materials proved inadequate.
Lieutenant Colonel Harold R. Turner, U.S. Army Ordnance Corps, watched a group of civilian engineers attempting to test-fire a rocket motor constructed entirely from salvaged materials. The motor casing was made from surplus artillery shell casings, cut and welded together. The nozzle was machined from a block of steel scavenged from a demolished bridge. The fuel injectors were adapted from automobile carburetors. The ignition system used spark plugs from a 1937 Ford truck. It should not work. Every principle of proper engineering suggested it would fail catastrophically.
Turner wrote in his official report, "The assembled motor appears to be a mechanical impossibility. The components are mismatched, the tolerances are inadequate, the materials are substandard. I anticipate complete failure during ignition sequence." The motor ignited perfectly. It burned for 47 seconds, producing thrust within 5% of the calculated values. It did not explode. It did not disintegrate. It performed exactly as designed, despite being constructed from materials that no German engineer would have considered using. Turner's follow-up report was remarkable for its tone of surprised respect. The motor functioned successfully despite utilizing entirely improvised components. This suggests that American manufacturing flexibility and engineering adaptability may represent a significant advantage in rocket development. We are not constrained by the need for specialized materials or precision manufacturing. We can build functional systems from available resources. This is, I believe, a capability unique to American industrial culture. He was correct. To understand why Americans could build rockets from scrap metal when Germans could not, you must understand the difference between two engineering cultures. German engineering culture valued theoretical perfection. The ideal rocket was one designed from first principles, where every component was optimized for its specific function, where nothing was compromised or approximated. This produced magnificent machines. The V2 was genuinely a marvel of engineering, but it required enormous resources, specialized infrastructure, and perfect execution. American engineering culture valued practical functionality. The ideal rocket was one that worked, regardless of how inelegant its construction might be. If scrap metal was strong enough, use scrap metal. If automobile parts could be adapted, adapt them. If the design had to be changed to accommodate available materials, change the design. This difference was not accidental. It reflected deeper differences in industrial organization and cultural values. Germany's industrial system was hierarchical, centralized, controlled. Decisions about design and production were made by technical experts at the top and implemented by workers at the bottom. Innovation flowed downward. Workers were expected to execute plans, not improvise solutions. America's industrial system was more distributed, more flexible, more tolerant of bottom-up innovation. Machinists in workshops were expected to solve problems using their own judgment. Engineers consulted with skilled workers about how to manufacture complex components. Innovation could come from anywhere in the organization.
This made American manufacturing less efficient in producing identical products to exact specifications, but it made American manufacturing far more adaptable when conditions changed or resources were limited. And in war, adaptability matters more than perfection. John Patterson was a master welder. He had worked at Chrysler since 1928, building automobile frames, then tank hulls when the war began. He had never seen a rocket. He had no formal education beyond high school. He understood metal, welding, and how to make things fit together. In March 1944, Chrysler received a contract to manufacture rocket motor casings for a new anti-aircraft missile program. The specifications were complex. The tolerances were tight. The Army engineers who delivered the blueprints assumed the work would require specialized equipment and extensive training. Patterson looked at the blueprints for 10 minutes, then announced he could build the casings using existing equipment and techniques he already knew. The engineers were skeptical. The design called for specific welding procedures, specialized alloys, precise dimensional control. Patterson was proposing to improvise using standard automotive welding equipment and mild steel. Patterson's response, recorded in a supervisory report, was characteristically blunt. "I can make it work. Give me 3 days." 3 days later,
Patterson delivered 5 completed motor casings. They were tested under extreme pressure and temperature conditions. They passed every test. They were, in fact, slightly stronger than the original specifications required because Patterson had intuitively reinforced areas where he judged the design to be weak. The Army accepted Patterson's modifications and incorporated them into the official design. Chrysler went into full production using Patterson's techniques. By the end of 1944, the facility was producing rocket motor casings at a rate of 500 per month, using methods that had never appeared in any engineering textbook. This was the American advantage: skilled workers who could translate theoretical designs into practical reality, often improving those designs in the process. German rocket production, by contrast, remained constrained by rigid adherence to original specifications, even when those specifications proved problematic. The first indications that American rocket development was more advanced than expected came in late 1944 as Allied forces liberated France and pushed toward Germany. German intelligence officers captured American military documents describing guided missile programs, anti-aircraft rocket development, and experimental propulsion systems. Initially, these reports were dismissed as propaganda or exaggeration.
But as more evidence accumulated, doubt began to grow. Dr. Walter Thiel, one of Germany's leading propulsion specialists, received a disturbing intelligence summary. American forces had deployed a new anti-aircraft weapon, the T-220 rocket launcher, a truck-mounted system that fired multiple unguided rockets at incoming aircraft. The system was crude by German standards. The rockets were simple, solid fuel designs with minimal guidance. But the system worked. It was effective. And most disturbing of all, the intelligence report suggested the rockets were manufactured using improvised materials and converted automobile factories. Thiel wrote to his colleague Dr. Ernst Steinhoff, "I have reviewed the captured American documents regarding their rocket programs. The materials and methods described are completely contrary to proper engineering practice. They're using scrap steel for structural components. They're adapting automobile manufacturing techniques to rocket production. They are building guidance systems from radio parts and commercial gyroscopes. By all theoretical principles, their rockets should not function. Yet the field reports confirm they are operational and effective. I cannot explain this discrepancy." Steinhoff's response, dated November 15, 1944, revealed growing concern. "What you describe suggests the Americans have developed a manufacturing approach we did not anticipate. They are not attempting to match our technical sophistication. They are bypassing it entirely by lowering their engineering standards while increasing production volume. If they can produce functional rockets using improvised materials and simplified designs, they may achieve numerical superiority despite technical inferiority. This is deeply concerning." But both men still believed German technical superiority would prevail. The Americans might produce large quantities of crude rockets, but quality would triumph over quantity. The V-2 remained the world's most advanced missile. American rockets were mere firecrackers by comparison. This belief would persist until the spring of 1945, when direct examination of captured American rocket technology would shatter every assumption German scientists held. When Dr. Ernst Steinhoff stood in Tunnel B of the Mittelwerk factory reading the intelligence report about American rocket development, he was experiencing the beginning of a psychological transformation that would define the rest of his professional life. Within hours, American forces would arrive. Steinhoff and dozens of other German rocket scientists would be captured, interrogated, and eventually transported to the United States under Operation Paperclip, the secret program that brought German scientists to America to work on rocket development for the U.S. military.
But before that capture, In those final hours before the Americans arrived, Steinhoff made a decision that would later prove crucial to understanding the psychological impact of what German scientists discovered. He began writing a personal journal, not an official document, not a technical report, just his private observations, thoughts, and reactions to what he was learning about American rocket development. The journal, discovered in archives decades later, provides extraordinary insight into his state of mind. The intelligence reports cannot be accurate. They describe American rocket programs using salvaged materials, improvised manufacturing, workers with no specialized training. This is impossible. Rockets require precision. They require specialized knowledge. They cannot be built like automobiles. Yet the reports insist this is exactly what the Americans have done. I do not understand. Perhaps the reports are intentionally false, designed to mislead us. Or perhaps we have misunderstood something fundamental about what is possible. I have spent the afternoon reviewing every technical document we possess regarding American rocket development. The picture that emerges is deeply disturbing. The Americans are not trying to match our technical sophistication. They are solving the rocket problem through an entirely different approach. Where we use precision-manufactured components, they use adapted automobile parts. Where we require specialized alloys, they use common steel. Where we employ teams of trained specialists, they use ordinary factory workers. And somehow, incredibly, their rockets work. Not as elegant as ours, not as sophisticated, but functional, reliable, produced in quantities we cannot match. I begin to suspect we have made a catastrophic error in our assumptions about American capabilities. These journal entries revealed a man beginning to comprehend that everything he believed about technological development was incomplete at best, fundamentally wrong at worst. In May and June of 1945, approximately 1,600 German scientists, engineers, and technicians were identified by American intelligence as valuable assets for post-war military and civilian programs. Many were rocket specialists from Peenemünde and related facilities. They were offered a choice: work for the Americans or face uncertain fates in the chaos of post-war Europe. Most chose to work for the Americans. Dr. Ernst Steinhoff was among them. In September 1945, he arrived at Fort Bliss, Texas, where German rocket scientists were being assembled to work on American missile development programs. What Steinhoff and his colleagues encountered at Fort Bliss completed the psychological transformation begun in the tunnels of Nordhausen.
Steinhoff and a group of German scientists were taking to White Sands to observe American rocket testing. They expected to see primitive facilities, crude equipment, unsophisticated operations. What they saw was different. The facilities were indeed less sophisticated than Peenemünde. The equipment was simpler. The rockets were cruder in appearance. But the operation was efficient, professional, and producing results. Steinhoff watched American engineers prepare a rocket for testing. The rocket was called the WAC Corporal, developed by the Jet Propulsion Laboratory as a high-altitude research vehicle. It stood 16 feet tall, weighed nearly 700 pounds, and was designed to reach altitudes of 25 miles or more. The construction was astonishing. The body was made from thin sheet steel, rolled and welded together in sections. The nose cone was a simple cone of aluminum. The fins were flat plates of steel, bolted to the body. The entire structure looked like something assembled in a garage workshop, not a precision manufacturing facility. Steinhoff wrote in his journal that evening, "I observed the American rocket called WAC Corporal.
Its construction violates every principle of proper rocket design. The body is too thin. The welds are visible and irregular. The components appear to be salvaged from other equipment. The guidance system is almost non-existent, a simple gyroscope and some radio equipment. By German standards, this rocket should not fly. It should collapse under its own weight. It should tumble. It should disintegrate. Yet when they launched it, it flew perfectly. It reached an altitude of 43 miles. It transmitted telemetry throughout its flight. It returned scientific data. It accomplished its mission. I stood in the desert watching this crude rocket ascend into the stratosphere, and I realized something that will haunt me for the rest of my life. We were wrong. Not wrong about the theory. Not wrong about the mathematics. Wrong about what matters. The Americans do not care if their rockets are elegant. They care if their rockets work. And because they care only about function, not about aesthetics or theoretical purity, they can build rockets faster, cheaper, and in greater quantities than we ever could. We built masterpieces. They built duels. And in war, tools win. This realization, that pragmatic functionality trumps theoretical perfection, was deeply unsettling to German scientists who had been trained to value precision and elegance above all else. Over the following months and years, as German scientists worked alongside American engineers on rocket development programs, they came to understand the deeper reasons why American rocket development had succeeded, despite using scrap materials and improvised methods. It was not that Americans were better theoretical scientists. Many German scientists were equal or superior in pure theoretical knowledge. It was not that Americans had better facilities. Peenemünde had been far more advanced than any American facility. It was the culture, the approach, the fundamental assumptions about how engineering should be done.